Hello, this is Philip Myers of PEMY Consulting. This is the final module of the Strength of Materials series for tank engineers. Failure theory of materials is a complex subject where active research is still taking place, but it is not a new theory. Because failure theory is attempting to predict material failure based on the microstructural properties of materials, it is not surprising that failure theories are numerous and continue to proliferate. Essentially, for homogeneous isotropic materials, they can be broken down into two broad categories. The first category involves ductile materials like steel, for which we have interest. The second category is for brittle materials like ceramics, but which we will not cover. We will discuss the maximum shear stress theory, or Tresca theory, which is applicable to steel structures, and talk briefly about the maximum distortion energy theory, or the von Mises theory. To give you a little intuition about the theories we will touch on, let us first distinguish between two broad types of loads applied to solid bodies. One such load is called hydrostatic pressure. In this context, it means that if a solid object were submerged at some depth in a liquid, say water, where the pressure acts uniformly on all surfaces equally, then the only thing that happens is that the volume changes because all material can compress a little on the application of external forces. But hydrostatic pressure does not cause failure in ductile materials. It is the distortion from the original shape that causes failure. When there are shearing forces, the materials in the object distort from its original shape so that the atomic structure changes from slippage planes in the material, and the related failure theory is called the distortion energy, or von Mises theory. It's important to be able to visualize what shear does to a ductile material at the atomic level. Each dot is an atom, say iron. When enough shear force is applied to the block of iron, the columns of the atoms in the atomic lattice start to slip. They form a slip plane. In fact, you have already seen this phenomenon at the macro level as in the leaders lines in a simple tension test of steel, but we'll see it again in a few slides. Recall that what has been easily measured and reported for material failure is a stress-strain curve. Here we see the curve for a material like mild steel. The material is linear elastic up to the proportional limit. Then the material starts to yield. In tension tests, the stress state is uniaxial, but in the real world, objects are usually in a multiaxial stress state. We must relate failure in the uniaxial stress case to the multiaxial case, which we will do now. We learned in the previous segments that the maximum shear stress occurs at 45 degrees to the principal stresses. In this case, the principal stress is aligned on the axis. You can clearly see the leaders lines here forming at 45 degrees. The test specimen on the right is a photo of a sectioned and chemically treated specimen from a tension test that shows the formation of the slip planes. Here is a quick refresher on the Mohr circle, which we will need in the upcoming slides. The green dots show the principal stresses for a tension test where we have a uniaxial stress case. In the uniaxial state, the Mohr circle has one principal stress, sigma P1, which is the axial stress. The other normal stress is sigma P2, which is 0. At any given angle, theta, from the axial direction in the material, the stress state is represented by the two red dots on the Mohr circle, where you will recall that for a Mohr circle that the angle of the diameter must be 2 times theta. Using the triangle is an easy way to be able to write the formulas without memorizing them, and I won't go through that now since we have done that in previous segments. The maximum and minimum shear stresses are given by the vertical line. The maximum shear stress is shown at the bottom because we orient positive shear down. In the equations on the right, by substitution of normal stresses sigma 1 and sigma 2 equal to 0 into the maximum shear stress equation, we see that the shear stress is 1/2 of the yield stress at failure. Now we consider the biaxial stress state. The normal stresses can both be positive, as in the top left, they can both be negative, as in the top right, or be of the opposite sign, That is, one is tensile and the other is compressive, as in the bottom. For the same sign cases and taking into account 3D Mohrs circles, we see that the maximum shear stress is always 1/2 of the largest normal stress. But things change for the opposite sign case. The maximum shear stress is 1/2 of the sum of the absolute values of the two normal stresses as shown in the diagram and the equation. So what does this mean? The overview of the previous results is most easily visualized as in this diagram. There are 4 quadrants to consider. In this plot, I have normalized the stresses by dividing by the sigma yield. For the same sign case, if either normal or axial stress reaches the yield stress, then shear failure has occurred. So the horizontal and vertical lines represent the boundaries of failure for both quadrants 1 and 3. For quadrants 2 and 4, for the opposite sign case, when the sum of the absolute values of the normal stresses is equal to the yield stress, then failure occurs. The diagonal lines represent this case, and the overall shape is called the Tresca yield criterion based on maximum shearing stress. Failure occurs when the stress state goes out of bounds on this diagram. Recall hydrostatic pressure. If we consider failure to be caused by energy that goes into distortion and not into hydrostatic compression of the solid, then this is a fairly good measure of how much energy is due to shear stress. The distortion energy theory, also called von Mises theory, represents this concept. You can see the figure compares the Tresca and the von Mises yield criterion for the two-dimensional state of stress. Tresca's yield surface lies inside of the von Mises criteria. Therefore, the Tresca's yield criterion is slightly conservative when compared to the von Mises yield criterion. For tanks and vessels, the von Mises criterion fits the experimental data more closely than Tresca's, but usually Tresca's yield criterion is simpler to use in elementary manual calculations. However, finite element analysis programs typically report the von Mises yield criterion for stresses because it is a mathematically continuous curve and the programs have sufficient computing power. This concludes our series on strength of materials for tank engineers. It's a fascinating and mathematically rich topic, and I would encourage you to get some good textbooks and study them to improve your understanding, appreciation, and enjoyment of the topic. We will see you soon in the next series. Thank you.